In this next lesson, we're going to be talking about chapter 5.3. The lesson is called Properties of Logarithms. So in this lesson, we're going to be showing you how to take advantage of different properties, and the first one being the change of base formula. Now, also, I'm going to be providing for you some videos of proofs of some of these formulas. And I feel like these proofs, when you see them, it just gives you more to rely on and recognize the fact that you can manipulate logarithms and find exponents of different bases, with some confidence because you understand and know that these properties are proven. So this is lesson 5.3. It's properties of logarithms. And we start with this idea of the change of base formula. Now, the way that they're presenting it here is that the change of base formula is being shown if you're just talking about base b. So take a look at what we have here. They're saying let a, b, and x be positive real numbers such that a is not equal to 1 and that b is not equal to 1, then log base a of x can be converted to a different base as follows. So let's follow along here and see what they're talking about. So here's using base b. So we're changing an expression, log base a of x, to what would it look like in log base b? Well, change of base formula says that if I go log base b of x and divide that value by log base b of a, where a is the base of the previous expression, then I will get the same answer as if I took log base a of x. Likewise, if we change that idea to base 10 now instead of base b, we can pretty much use the common logarithm key, and so you just use the log key on the calculator. So if I start off once again with log base a of x and say that that's equal to now log of x divided by log of a. And we'll be demonstrating that in a little bit. But before we move on, I want to just say we can also use this. And you'll remember I told you the story about me and my super duper calculator TI-89 that only had an ln key and it didn't have an log key. Well, so this is what I used right here, was this idea right here that we can use base e now, because ln, remember, is the natural log, where it's the same as saying log base e of x. Well, so let's see how this works. If I use log base a of x, where a is just some arbitrary positive number, I can actually find what log base a of x is if I just convert it to ln of x divided by ln of a. Or I'll say it again, just natural log of x divided by natural log of a. So here in example 1, we're going to be using the change of base formula using common logarithms. So look at what we have here. We're saying log base 4 of 30, and we can actually rewrite that then as log of 30 divided by log of 4. And so if we do that, we'll punch that into a calculator. I'm going to divide log of 30 by log of 4. And I get 2.453445298. So we're going to demonstrate finding the log base 4 of 30 by using the change of base formula. And we're going to use it doing it with the log key. So we're going to say log of 30, and we're going to divide that by log of 4 and hit enter. And so I get 2.45344528. If I take 4 and I raise that to that value by hitting up arrow and hitting enter, notice it loads it up as the exponent, and hit enter, look at what I get. 4 to that exponent gives me 30 and a little bit extra, but it's not that bad. So good answer. Well, let's do it with natural log. So it should work because natural log is just base e, right? So log of 30 divide by log of 4, enter, and I get pretty much that same number. So let's just prove it again to ourselves. If I put 4 and raise it to that number and hit enter, I get 30. So there you have it. That's the demonstration of the change of base, actually both in common logarithms and in natural logarithms. We started out with log base 2 of 14. So I'm going to do it with common logs first. We'll say log of 14, and we'll divide that by log of 2. And hit enter. We get 3.807354922. That's the exponent, right, of 2 that will give me 14. Let's see if that works. So if I take 2 now and raise it to that exponent and hit enter, I get 14. Let's see if we can get that to work with natural log. If I do natural log of 14 and I divide that by the natural log of 2, I get 3.807354922. Now, if I took 2 and I raised that to that exponent by hitting up arrow and hitting enter, I get 14. So that's a proof that the change of base formula works both in common logarithms and in natural logarithms. So here's example 3, where we're going to actually be using some of the properties of the logarithms. And we're going to write each logarithm in terms of ln of 2 and ln of 3. So notice ln of 6. Well, ln of 6 can be actually rewritten as ln of 2 times 3. And so since that's the case, then I can write it as ln of 2 plus ln of 3. And we're done with example 3A. So here's B. If I took ln of the quotient 2 over 27, and also recognize that 27 is the same as saying 3 times 3 times 3. Let's see what we can do here. We can actually say that this is, first of all, ln of 2 minus ln of 27. Or we could actually say it this way. So ln of 27 can be written as ln of 3 plus ln of 3 plus ln of 3. But we have an ln of 2 in front of that. If we distribute that, and actually, or we could just add those together, we can actually write this now as ln of 2 minus 3 ln of 3. And so that is the same as saying ln of 2 over 27. Here in example 4, we're actually using the properties of logarithms to verify something. So in this statement here, they're saying we've got the negative log base 10, so it's common log of 1 over 100. And that's the same as saying the log of 100. Well, let's just work at this a little bit. We know already that I can rewrite this as log on the left-hand side of 1 over 100 to the negative 1 power, because I can just take that negative 1 from the front of the logarithm and make it the exponent of the argument inside the log. So if I say that, then that's 1 over 100 to the negative 1 power, which is of course the same as saying 100. So that's log then of 100, which is equal to the log of 100. And if we want to take that further and just go ahead and evaluate those logs, we know that the log of 100 is 2, because 10 to the 2 is 100. So 2 is equal to 2, and there we have it. Here in example 5, we're just going to expand logarithmic expressions. And so here's just a couple more that show that we can expand these. So here we go. This is saying for a, log base 4 of 5x to the 3y can be written, first of all, as log base 4 of 5 plus log base 4 of x to the 3 plus log base 4 of y. Now we can further work this, because I can use the third property and rewrite the middle term here, taking that exponent of x and putting it in front. So 3 log base 4 of x, and everything else just copies down. So and I lost a plus sign there, so I'll put it right back in. So there's A. That's A expanded. Let's do B. So B is natural log of square root 3x minus 5 over 7. Well, that can be rewritten as the natural log of 3x minus 5 to the 1/2 power over 7. And according to our properties, we can write that as the natural log of 3x minus 5 to the 1/2 power minus the natural log of 7. Further, that can be written as 1/2 natural log of 3x minus 5 minus the natural log of 7. And we're done. So just like we can expand logarithmic expressions, we can also rewrite them by condensing them. So that's what this example is about. And so let's just go ahead and do these in front of you. So this says for A, I have 1/2 log of x plus 3 log of the quantity x plus 1. Well, I'm going to go ahead and use that power rule first. This can be rewritten as log of x to the 1/2 power plus log of x plus 1 raised to the 3. And then I can rewrite that as log as x to the 1/2 times x plus 1 to the 3rd power. And so there's A. Here's B. B says 2ln, or 2 log of x plus 2 minus natural log of x. So we can write that, the first part, as natural log of x plus 2 to the second power minus the natural log of x, which can be written natural log of x plus 2 raised to the 2 divided by x. And so now it's one term. For C, it says 1/3 of the entire quantity of log base 2 of x plus log base 2 of x plus 1, like that. Well, we can drop that outer parentheses by distributing that 1/3. And so if we do that, I can say 1/3 of log base 2 of x plus 1/3 log base 2 of x plus 1. And then further, we can call this log base 2 of x to the 1/3 power plus log base 2 of x plus 1 raised to the 1/3 power. And then to finish it off, log base 2 of x to the 1/3 power times x plus 1 to the 1/3 power. So there you have it. You've been shown in the examples several ways of condensing and expanding and doing log properties. And so here is your homework for section 5.3, Properties of Logarithms. And so give these 22 problems a try, and we'll see you next time.